Hello, everyone, and welcome to the fourth lecture on the GloVe embedding model. In this lesson, we're going to build a simple GloVe model from scratch. Over the past 3 videos, we've explored the core ideas behind GloVe, learned how to construct a co-occurrence matrix, and derived its objective function, while examining the detailed architecture of the model. Now it's time to put everything together. Using the concepts we've learned so far, we'll implement a complete GloVe model from scratch using Keras. Let's get started. We'll use the following small corpus to build and train our GloVe model. The first step is to build a vocabulary from these sentences. To do this, we use Keras' tokenizer class to tokenize the corpus. The fitOnTexts method scans the entire corpus and builds an internal vocabulary. It also assigns an integer index to each word based on its frequency. The tokenizer stores this vocabulary in the word index attribute as a Python dictionary. The resulting word-to-index mapping looks like this. This dictionary represents our vocabulary. Next, we create another dictionary that maps indices back to words. The resulting index-to-word mapping looks like this. Next, we convert each sentence into a sequence of integer token IDs using the text-to-sequences method. The resulting token sequences are shown here. All 10 sentences in the corpus have now been converted into sequences of token IDs. Next, we determine the vocabulary size. Notice that token IDs in the vocabulary start from 1. The token ID 0 is typically reserved for padding. Therefore, we add 1 to the size of the dictionary so that the vocabulary size also includes token ID 0. Next, we construct the co-occurrence matrix from the corpus. In this example, we use a symmetric context window with a size of 10. We also enable distance weight decaying. Next, we set the embedding dimension to 2. In practice, the embedding dimension is typically around 300. However, since this is a simple demonstration, we choose a 2-dimensional embedding space to make the learned word vectors easier to visualize. Instead of storing the co-occurrence matrix as a dense matrix, we represent it as a Python dictionary. This is much more memory efficient because most entries in a co-occurrence matrix are 0. Now let's process the corpus one sentence at a time and update the co-occurrence dictionary using a sliding context window. First, we determine the left and right boundaries of the sliding window. Let's use the first sentence as an example. This is the token ID sequence for the first sentence. At the beginning of the loop, I is 0 and center ID is 1, which is the token ID of the center word, or target word. The left boundary of the window is computed using the max function. Since I minus the window size is negative, start becomes 0. Next, we compute the right boundary using the min function. The last valid index of this sentence is 8, while I plus the window size is 10. Therefore, n becomes 8. Since we're using a symmetric context window, we scan both the left and right sides of the center word. Next, we iterate over every context position between start and end. If the current position is the center word itself, we simply skip it. In the next iteration, I is 0 and j is 1. The token ID of the context word, context ID, is 8. The distance between the center word and the context word is simply the difference between their positions, so the distance is 1. Since distance weight decaying is enabled, the weight is computed as 1 divided by the distance. Because the distance is 1, the weight is simply 1. Finally, we add this weight to the corresponding entry in the co-occurrence dictionary. Repeating this process for every sentence in the corpus completes the construction of the co-occurrence dictionary. Now that we have the co-occurrence dictionary, the next step is to generate the training dataset. Here, I and j represent the indices of the target word and the context word, and y represents their co-occurrence count. We store I and j as the input features and y as the target value. Using these lists, we construct the training dataset and then shuffle it before training. The resulting training dataset looks like this. Next, let's define a custom class that builds and trains our GloVe model. As we saw in the previous video, the overall architecture of the GloVe model looks like this. The model contains 2 embedding matrices, one for the target words and the other for the context words. It also includes 2 bias vectors, one for the target words and one for the context words. Each embedding matrix has a shape of V by M, where V is the vocabulary size and M is the embedding dimension. Each bias vector has a length of V. Next, we define the call method. Later, when we train the model using the fit function, the input feature matrix xtrain will be passed to the inputs argument of this method. The first column of inputs contains the token IDs of the target words, while the second column contains the token IDs of the context words. Next, we retrieve the embedding vectors and bias terms for both the target and context words. WI is the embedding vector for the target word, and VJ is the embedding vector for the context word. Similarly, BI is the bias term for the target word, and BJ is the bias term for the context word. Finally, we compute the dot product of WI and VJ, add the 2 bias terms, and return the result. Recall from the previous video that this value corresponds to the model's prediction of the logarithm of the co-occurrence count. Next, let's define the train step method, which performs one training step of the GloVe model. Later, when we call the fit function, each mini batch of training data is passed to the data argument of this method. Here, x represents the input features and y represents the target values. Now we're ready to compute the gradients of the loss function. First, we pass x to the call method to obtain the model's predictions. These predictions correspond to the estimated logarithms of the co-occurrence counts. Next, we compute the weighting function f of y using the actual co-occurrence counts. Recall that f of y is defined by the weighting function we derived in the previous video. Now we compute the loss by comparing the predicted values with the actual logarithms of the co-occurrence counts. Once the loss has been computed, TensorFlow automatically calculates the gradients using automatic differentiation. Finally, we apply those gradients to update all trainable parameters of the model, including the target embeddings, the context embeddings, and the two bias vectors. After each training step, we return the loss so that we can monitor the training progress. Finally, let's define a method that returns the embedding vector for a given word. Recall that after training is complete, the final word embedding is obtained by adding the target embedding vector and the context embedding vector. Therefore, this method simply returns the sum of those two embedding vectors. Now we're ready to train the model. First, we create an instance of the GloVe model. The embedding dimension is set to 2 and the maximum co-occurrence count is set to 100. In the original GloVe paper, this parameter is denoted by Xmax. In our implementation, however, we use Y to represent the target value, so we name this parameter Ymax instead. Next, we compile the model using the Atom optimizer. The original GloVe paper used Adagrad, but in this implementation, we use Atom because the loss decreased faster and more steadily for our small demonstration model. It's also worth noting that the original GloVe paper was published in October 2014. At that time, Adagrad, introduced in 2011, was already widely used, whereas Atom had not yet been published. Atom was introduced 2 months later, in December 2014. Therefore, it seems that the original GloVe authors used Adagrad simply because Atom had not yet been introduced. Finally, we train the GloVe model using our training dataset. Once training is complete, let's first take a look at the training loss. We can also retrieve the embedding vector for any word in the vocabulary. For example, here is the two-dimensional embedding vector for the word king. As you can see, the training loss decreases steadily over time. This indicates that the model has successfully learned from the training data. Next, let's visualize the embedding vectors for all the words in the vocabulary in a two-dimensional space. The result looks like this. Since we trained the model on a very small corpus, we shouldn't expect this visualization to reveal meaningful semantic relationships. With a much larger corpus, however, words with similar meanings would naturally be located closer together in the embedding space. I won't go into the plotting code here, since our focus is on understanding and implementing the GloVe model itself. Now let's run this code and see what we get. Here are the results. In this video, we implemented a simple GloVe model from scratch using Keras. Along the way, we built a co-occurrence dictionary, generated the training dataset, implemented the model architecture and custom training loop, and finally trained the model to obtain word embeddings. Although this example uses a very small corpus, the overall implementation follows the same principles used in the original GloVe algorithm. In the next video, we'll move on to another count-based word embedding model called Swivel, proposed by the Google research team in 2016. We'll explore how Swivel addresses some of the limitations of GloVe and introduces a different approach to learning word embeddings from co-occurrence statistics. Thanks for watching, and I'll see you in the next video.